152. There's like a little section in there for us if you want to stop by. We'll be meeting today too. This semester we're trying to get some projects done. We have someone building an AI to play, it's a kind of like a Risk clone, and there's a contest that we're entering, and it has a grand prize of $1,000. So if anyone's interested in helping build that, let us know. We can get you on that. We're building a database with Professor Schuster for some crisis resources, things like shelter, food, medicine, yeah. So if you want to work on that, if you have any experience with a database, it'd be really helpful, and it's really something that would look good on a resume. And then we're hoping to get some funding this semester from Mesa and holding our own contest for a debugging bee, we're calling it. We're going to be using Arduino bots for that. If you want to learn how to use an Arduino bot, it's a great time to learn. And then we're building a website, so anyone with website experience, we're also looking for that. If you're interested in any of these, even if you don't feel like you have the skill level, come in, talk to us. We can teach you new things, and if you do have the skill level, we really appreciate the help, and it would look really great for any college applications or future work experience you want to have on a resume. You write down our times. We go from 12 to 3, and we are in the room 152. And that's in the liberal arts department.
It's right there across the fountain.
And you do not have to be present for all 3 hours or every day. We meet Tuesdays and Thursdays, so twice a week. We don't need a 6-hour commitment. Just stop by whenever you have time. Thank you.
All right. Thank you, Kevin. All right. So what we'll do today with the class is we're going to finish up binary number addition.
Tuesday and Thursdays.
And we do have a homework assignment, already up here. You have 1 week to finish this homework assignment. It will involve things that I'm going to talk about today. So you might want to kind of pay attention today and just kind of, as we talk about those topics, see if you can relate today's lecture to the homework assignment, because that's the usual things that I do, that I would give you a homework assignment on something that I'm going to talk about, so that people would kind of stay focused that way. Okay. So the first thing I do is to take a look at the homework assignment, so you know what you are expected to do, and then we'll go back and talk about the topics. All right, so let's zoom in just a little bit more. So in this assignment, we want to use LogicSim to create a 3-bit by 3-bit, which means the inputs will be 2 3-bit numbers using carry look ahead and not carry ripple. Last Thursday, I gave you guys a carry ripple adder in the lab. So that is not what we're looking for. We're looking for something that is new that we'll be talking about today. When you're done, you want to save the file and turn in the LogicSim file as the submission of this particular homework assignment. Canvas will have an interface for you to upload the file. I want you to name your submission file after your last name plus your first initial. So in the case of myself, I will be Auyung, A-U-Y-E-U-N-G, which is my last name, and T is my first initial, and then .circ, because .circ is the extension of LogicSim files. Is that okay so far? Okay. So the interface to the design would involve 3 input pins. 2 of the input pins, X and Y, are 3-bit input pins. So up to this point, we have only used single-bit pins. In this homework assignment, we'll be using multi-bit pins. Okay. In today's lab, I will be going over these things using example programs and stuff like that. So make sure you don't miss today's lab, because I will be using the lab time to show you how to use LogicSim to get at least the input-output done. Label these 2 3-bit pins as X and Y because they represent the numbers that we are adding. The 3rd pin is going to be a 1-bit pin. This is the carry input, and we'll call this C in for carry in. Yep.
Are the 3-bit input pins, are they made up of the single input pins and just structured to be 3 of them?
Nope, you'll see in the lab time, it is a single pin, but it has 3 bits. So it is one single pin, you pull one pin out of the tools, and you put it onto the design, and then you change the property to 3 bits instead of 1. 1 is the default, but we want to change it to 3 bits. Outputs. There are 2 output pins. One is a 3-bit output pin, which is representing the sum of X and Y. So I want this one to be labeled as S. The other one is an overall carry output. So I want you to label that one as a C out for carry out. So are there any questions about the pins, coming in and going out of the design? The pins are basically kind of like parameters to a subroutine. It defines the interface to whatever you're doing in the inside. So input pins are kind of like passed by value parameters, and then the output pins are kind of like passed by reference parameters, so that you can update and reflect the result after some computation. The general guideline. Okay, so I'm not going to talk about the general guideline just yet, because we do have, these terms that we have not introduced yet. So we'll leave it as, like this for now, and then we'll switch gear, back to talking about the adding. So we are pretty much done all the way to here. Okay. So we'll start with section 6 today, inside this particular module. This is a rather long module because it started off with addition in base 10, and then I dissect, the multiple components of, multi-digit addition and stuff like that. So that's why it's kind of long. But it's only when we get to here that we start to look into, maybe it's not here. I think it's not here. It is, okay. So when we get to here, then we start to talk about the inefficiency of the previous approach. How many people still remember the carry repo design from last Thursday? Or at least, or at least in theory, what is not so good about it?
Takes a long time to run because you have to rely on the previous output before you can process the next one.
Okay, if we have to rely on the previous output, yes?
Oh yeah, that's what I was going to say.
But which output, which particular bit is being propagated?
Carry.
The carry bit. Okay, very good. So the carry output of one column needs to be settled, needs to be correct before the next column has the correct input to start. So, it's not like, the thing is going to blow up, because the carry input is not correct. It's just that it won't settle. It won't give you the correct result until the carry has been propagated throughout the entire adder. Okay. So that's one problem of that particular design. So what we'll do today is to talk about a new design, or a design that's based on the carry repo design, but it doesn't have that disadvantage. Okay, so this one theoretically has constant time carry calculation. If you want to figure out what is K1, which is the carry bit of bit 1, it will take constant time. If you want to figure out what is K64, when you have a 64-bit adder, it will take the same amount of time. Okay, so you don't have to wait until K1 is done, go through a whole bunch of logic, and then K2 is done, then go through a whole bunch of logic, K3 is done. It's constant time. Okay, which is great because if you're Intel or AMD, you want your processors to be able to perform calculations as quickly as possible. So this allows designs that can have constant time addition and not something that is proportional to the width of the integer. So all this stuff here, so far is really just changing the notation. So instead of using K and then bracket I plus 1, I now switch to K subscript I plus 1. Okay, it's just a notation change because otherwise it takes up way too much space, so I don't want to deal with it that way. All right, so we'll start with this long derivation here. Okay, it looks like it's kind of difficult to understand, but it's not. Okay, so we'll go take a look at each row and figure out, okay, why is it like that? Okay, so let's take a look at the first row. K I plus 1, which is the carry bit to column I plus 1, or bit I plus 1, is C xi plus C qi. What is that representing? Let's focus on these things just one thing at a time. What is this representing? I hope you still remember the notation from last week's discussion.
The carry function given x and 1.
Yep.
xi.
Yep, which basically means it is the carry of xi plus yi. Not the result, just whether we have a carry or not from the addition of xi, yi. Okay, very good. So that's one way to contribute to the carry of bit I plus 1. But there's one more. Because when you look at the sum, qi is the result bit of xi, yi, but that needs to be added to the carry to column I itself. So that second addition can also have a carry. And as a result, we have to somehow say, okay, we can have one carry from adding the numbers that you're given. We can also have a carry by adding the carry of column I to the result of adding xi and yi. So either one of these, or at least these two can contribute to the carry of column I plus 1. So this plus here is a logical OR. Okay, I use the notations. I borrowed the notations from arithmetics, but these are all Boolean operations. Are we still doing okay so far, or do you guys need to go back a little bit to talk about what is the C function and what is the Q and so on? It's all good so far? All right. Okay, so if you have questions about those things, it might be indicative that you just need to review the material a little bit over the weekend, like prior to the class, so that you can kind of remind yourself what we have learned already up to this point. Okay. What about from here to here, from the first row, this expression here, to this expression here? Now you can pretty much see that C of xiyi becomes xiyi, and then C of qiki becomes just qiki. How did that happen? What makes this happen? Going from the first row to the second row.
The way that you add them or something like that.
You wouldn't you only get a carry bit if it was x and y were both 1?
Right. So xiyi is a conjunction. Remember, these are all Boolean operations, and I'm borrowing the concept. I'm borrowing the notation of multiplication to mean conjunction. So xiyi is really xi and yi. Why is that replacing carry of adding xi and yi? This is also from last week. I know the weekend is long. Okay, but why?
They need to both be 1 in order to have a carry.
Exactly. Okay, so that's how we defined the carry function. Okay, so the carry function is defined to be the conjunction of the two bits that you're adding. If both bits that you're adding are 1s, you will need a carry in base 2 because there's no single digit that can represent the quantity of 2. That's why we change from C xiyi to xi times yi, which is xi and yi. These are Boolean operations. All right. Okay. Same thing for qiki, because the top row has the carry bit of adding qi and ki. So the bottom row or the next row just says, okay, let's expand the function. It becomes qi and or conjunction ki. Are we okay so far with the first row to the second row? Okay. From the second row to the third row, okay, what changed? qi is expanded to the result of adding xi, yi. How did that happen?
That's how Q is defined.
It's the definition of qi. Okay, if you look a little bit further up in the notes, that's how qi is defined. Okay, all right. So, sorry?
Section 4.
In section 4, thank you. All right, so what about this one? From the third row to the fourth row. The only change from the third row to the fourth row is r xiyi becomes xi not yi, or not xi yi. How did that happen?
That's just another way of writing and.
No, but r is not and. R is different, right? We use and for carry, but r is different.
Isn't that?
Yeah, go ahead.
You're expanding the result.
We're expanding the result. Okay, we talked about how the result is exclusive OR, but I was stubborn not to use anything other than the common operators. So this is how you can express, exclusive OR. using just regular negation, conjunction, and disjunction. Is that okay? All right? And exclamation point means negation. Okay, it means logical not. All right. What about from here to here?
Just distribute the K and
We're using distribution. Very good. So as it turns out, the rule of, or the law of distribution also works in Boolean algebra. In fact, it works in both ways. Okay, it only works in one way in arithmetic, but in Boolean algebra, it works in both ways. So you can distribute conjunction over disjunction. You can also distribute disjunction over conjunction. Okay. But that's okay. You know, in this case, we're only distributing the conjunction over disjunction. Okay. What about from here to here?
Well, that doesn't change any meaning. That just adds an and.
We're just adding an and true,
And
right?
true, so it's still true
Yep.
in the same ways.
Yep, it preserves the value. It just looks a little bit longer. Okay, so it is the same thing like in arithmetic. In arithmetic, if you multiply one to anything, it doesn't change the value, right? In Boolean algebra, if you say and true, it doesn't change the value of the original thing. Okay, so it's the same thing. But when I say that, you guys are supposed to say, I'm not sure about that. Can you prove that? Okay, can you prove that, you know, true is the identity of conjunction? So how do we go about proving that? Okay, so here's x, which is an independent variable, okay, and here is x and true. So we separate these into two different columns. X as a Boolean variable can be false, can be true. When x is false, what is false and true? False. When x is true, what is true and true? True. Very good. So now we can see that these two columns are the same for all possible cases, which means they are the same. They're equivalent. Is that okay? So anytime you see a Boolean expression, you can always say and true and append as many times as you want. And true, and true, and true, and true, and true. Okay, it doesn't change the meaning at all to the conjunction. Is that okay? All right. So why would we want to do something like that? Well, so that we can do something like this, okay? Now, this is something that looks really weird if you look at this as arithmetic algebra, but remember, we're dealing with Boolean algebra, not arithmetic algebra, okay? So when you have true, you can change true to become true or whatever. It doesn't matter what that whatever is. It doesn't change the meaning of true. Does that make sense to you? Okay? True versus true or x is still true. Because in order for a disjunction to be true, at least one side needs to be true. So if you have a constant true on one side, then the expression is guaranteed to be true anyway. Okay? So it seems like I'm making this more complex for no particular reason. From this row to this row here, what am I doing? I'm just distributing, exactly. Okay, so the 1 goes to the left-hand side, the ki goes to the right-hand side. So by doing this, I'm introducing a new term in the disjunction, okay? This term was not there to begin with, and it is now there. From this row to this row here, I just replicate it, okay? So there's one or xi, yi, ki here, and there's another one here. This one is new. So there are two versions of the same thing. Here's one, and here is another one. Now, once again, if you look at this from the arithmetic perspective, it doesn't make sense, okay? But from the Boolean perspective, it's fine. Because if you have an independent variable x, what is x or x? You get x back. So you can say x or x or x or x as many times as you want, and you still just get the original x back, right? So this is exactly what I'm doing. I have this thing here, and I can replicate it as many times as I want in the conjunction and not change the value of the conjunction itself. Is that okay? All right? Okay. So I position these things very carefully, because now I can put parentheses around this guy and put parentheses around the other one, okay? By the addition of the extra parentheses, I am using the rule of associativity. In other words, with addition or disjunction, in this case, I can change the ordering of evaluation, but it doesn't change the actual value of the expression. Okay, so that's why I can put parentheses in any way I want, and it will still preserve the values. Are we still doing okay so far? Okay, excellent. How may I help you?
Did you find a flash drive up here?
Flash drive.
Oh, it's right
Oh,
there.
right there.
It's right there.
It's still attached.
I had too much fanatic going on at 9 o'clock at night. Too many people talking to me.
Okay,
Thank you.
no
Sorry
problem.
about
That's all right. So now when you look at this expression here, okay, you can see that both conjunctions have some common components, right? xi is common to both of the conjunctions, and ki is common as well. So I can do factoring now. Okay, so I pull those out into its own term, and then whatever is left, whatever is different, which is yi from the first expression, goes here, and not yi goes here. So I'm using factoring, okay, just like you would with regular arithmetic. The other one is the same thing, except I'm factoring yi ki, and I'm left with xi or not xi. But then when you look at yi or not yi, what is that? It can simplify to true, because when you look at a independent Boolean variable and the negation of that, and you say, I want a disjunction of those two, one of them is guaranteed to be true, and the other one is guaranteed to be false. But with a disjunction, if at least one side is true, the whole thing is true, which means this has to be true. Okay, there's no way this expression can be false. So this becomes true, and this becomes true as well. But when you say something and true, okay, we can simplify that and just not say and true. So we get rid of the one, we get rid of the one, and then with these two terms, okay, with these two terms, you can see that ki is common. So I factor out the ki, and I'm left with xi plus y, or xi or yi as the only part that is left. Are we doing okay so far with all these derivations? Now in this class, we are not required to do all the derivations. Okay, this is not a class about proving theorems or using Boolean algebra like this. Okay, in 440, we do that. Not in 310, but in 440. So even though I won't give you, something like this, okay, even though I won't give you something like, okay, start with ki plus 1, and you prove that ki plus 1 equals to this term, you are not going to get questions like that in this class, because this class is not about proving theorems. Yep?
So if we would have like a problem that requires the use of this, do you want us to just skip to the end?
Yeah, you can use just the result of the whole derivation. You do not need to derive it. Okay? But I do want to go through the derivation because I want to at least give you an exposure to Boolean algebra. Okay? Some of you may not use Boolean algebra at all after this class, after you graduate from a 4-year university, because you will see this stuff again in other classes. But some of you, if you want to become a computer engineer or a electrical engineer, you would use this stuff on a daily basis. Okay, this is going to be very, very useful to you. So I do want to give you at least some exposure, and on top of everything else, I cannot teach a concept unless I can prove it can go from the top to the bottom. I cannot just say, yeah, Wikipedia says so. Okay, so this is partly to satisfy my own curiosity as well as my own desire to make sure that I can derive it. So after all these steps, we still have a ki. In other words, the carry-ripple problem is still there, okay? Because ki plus 1 still depends on ki. But the expression looks a little bit different, okay? So when this expression looks like this, then I'm going to define two terms, okay? I'm going to define the term called gi. Gi is nothing more than just the conjunction of xi and yi, okay? Just xi and yi, nothing more than that. Pi, on the other hand, is nothing more than xi or yi. Nothing more than that, okay? A simple gate can do this. So by using these two terms, okay, as you can probably expect, I can now change this expression by using GI and GI and PI. It becomes this term here. Okay, it's just substitution, right? Any questions up to this point? And then somebody's going to say, oh, but we still haven't gotten rid of the problem of the carry ripple because, hey, Ki is still on this side. We still rely on the carry of the previous column. So it would seem that we haven't solved the problem yet. Okay, fine. So whenever we have a problem like this, then we go, okay, let's go ahead and expand out and figure out what is K1. Now, when we want to figure out what is K1, what is I? When you look at the original general description, if I want to figure out what is K1, what do you think I should be?
0.
I will be 0. Very good. So we plug in I equals to 0 to the rest of the expression. Then we get K1 equals to G0 plus P0 K0. Does that make sense to you? Okay. Cool. No problem. Then we try to figure out what is K2. When we try to figure out what is K2, we expand because when you want to figure out what is K2, I equals to 1. So we expand K2 and that becomes G1 plus P1 K1. But we know what K1 is already, don't we? From the previous equation. So you plug in what is K1, or you substitute the actual expression of K1 in place of K1. Then we get something like this. Okay? But then you can also apply distribution. So we end up with something like this. Is that okay? So now we know what is K2. What about K3? We use the same approach. We plug in and say that, okay, if we want to figure out what is K3, we need I to be 2 in the original, structural equation. So we ended up with K3 equals to G2 plus P2 K2. But we know what K2 is at this point, don't we? So now we can substitute, right? We can substitute and say, oh, K2 is this big gigantic mess here. So instead of using K2, we use that gigantic mess. But then you can use distribution again, and then you end up with an expression like this. So now we know what K3 is. Is that okay? And you can probably imagine, if you need to figure out what is K100, okay, you just have to figure out everything from K1 all the way up to K99. Then K100 is going to look something like this, but it's going to be a little bit more complicated. Is that okay? So is the general approach okay with you guys? Yeah. But when you look at this K3, does it refer to K2? No. All the terms that it does refer to are the G's, the P's, and K0. If you are to calculate or estimate how much time or how many gate levels is needed to compute K3, what would be the amount of time or gate levels to do it? The first level is going to be doing what? The first level would be the G's, right, and the P's. So the G's and the P's are based on the X and the Y's, right? So this is one level of gate logic. Is that okay? Once we have the P's and the G's, and K0 is available to begin with because it is one of the inputs, then we have all the conjunctions to deal with. So the next level up will be all the conjunctions. When you have the results of all the conjunctions, then we have one gigantic disjunction on top, which is our last operation. So you are looking at 3 gate level propagations. It doesn't say the 3 gates, okay? And we are talking about 3 levels of gates, because many things can happen at the same time at each level of calculation. Is that okay? But it is true for K2 as well. Okay, K2 is also only reliant on G1, P1, G1, P1, P0, K0. So it also has 3 levels of gate propagation. What do you think about K100? 3 levels of gate propagation. Now you do have a lot more going on in each level, but it will still be only 3 levels of gate propagation. Is that okay? I mean, are you guys kind of convinced that this approach can give us what we want? Because we want it to be able to compute k whatever without using the carry ripple approach. There's no rippling anymore. Are we doing okay so far with this? No one seems to be impressed. It's like, wow. Okay, we solved that problem. It's a big problem that we need to take care of. This solve that problem. So, if I just ask you what is K100, what are you going to do? If I tell you that you can use a program to figure out what is K100, what would you do? Would you go from K1, K2, K3 all the way up to K99 and then expand that? Yeah, go ahead.
Is there? That's kind of like what I had in the back of my mind was: is there an easier way to obtain K99 than K2?
What do you think? Do you see? Okay, one thing that can tell whether someone has the knack or the natural talent or the inborn ability to become a good programmer is whether that person can figure out patterns, can see patterns. Okay, you can say, oh, I can see a general pattern here. So do we see any pattern between K3, K2, and K1, and how they expand? Do you see a particular pattern? There's definitely a pattern of some kind. Okay, because all the terms seems to go. If you're trying to figure out Ki plus 1. All the terms seems to have Ki or Gi, okay, and then you have Pi, Gi minus 1. So you can see 2, 2, 1, 2, 1, 0, 2, 1, 0, 0. Yep.
Is it the addition of just as P, like the subscript something? It looks like just the incrementation of just the P.
Yep.
What goes out.
Yep.
Bottom level.
Yep. So there's definitely there's a certain pattern. You can see G2, G1, G0.
So G increases by 1, and then you add P according to how much.
Exactly. You pad all the P's so that you have the entire sequence of numbers, right? And then the other one, this one is kind of on its own because you have K0 and then you have all the P's up to that point. There's no G in the last term. Yep.
And that last term, wouldn't that always just be 0? If K0 is 0?
It's always K0. It is always K0. Because K0 is an input pin, which means it's not computed. There's no propagational delay of any kind to get K0.
Okay, but isn't K0 always just false? Like, isn't
No,
it?
K0 is not always false because you want your adder to be able to take in a K0 as an input pin. So even most of the time, we want it to be 0 to do the calculations. Occasionally, you might be using the leftover carry of a previous addition as your carry in. So you can extend the width of your adder by stacking, the add operations. Okay, so K0 is generally used as an input pin, even though most of the time you want that to be a 0. But occasionally it is not a 0, it is the leftover carry from the previous addition. Okay? All right, but we definitely see a pattern here. Whenever we see a pattern, then we want to generalize, okay? And this is the generalized form. K subscript n plus 1, okay, is, the big E is OR operations, kind of analogous to the sigma for summation. The big wedge operation is kind of like a pi. It's a multiplication, or in this case, it becomes a conjunction of the subterms. And then you can see how I use index I to go from 0 to n here. This is a sub-expression of this, which means J starts with I plus 1 to go to n. Okay? And then this is not a regular plus, it is actually a OR, it's a disjunction. And then once again we have a big conjunction here. So this is just a huge conjunction involving everything from P0, P1, P2, all the way up to Pn. So this is the generalization based on the observation that we had with K1, K2, K3. Did we notice a pattern? this is the result of looking at the pattern and go like, oh, I think I see the general pattern and I can figure out what is Kn minus 1 using a closed form. So it doesn't rely on Kn anymore. Go ahead.
Could you just draw out like maybe n is equal to 3 of the first g term?
Okay, so let's go ahead and put this up on the screen like that. We also need the bound to be visible. Okay, there we go. That's what we can do here. And then we'll go ahead and try to figure out what is. Okay, so we'll use this to try to figure out what is K3. Okay, so one way to look at this is to say, you know, we'll use a programmatic way to look at this. How about that? Okay, so you say for I equals, okay, I'm not going to declare the variables. I'm just going to use a for loop here, just so that we can kind of equate this to something that you know already from your other classes. So I is going to go from 0 to n. In this case, is what? 2, because n plus 1 is 3, so we want n to be 2. So as long as I is less than or equal to 2, plus I, okay? And then what are we doing inside here? Well, you first start with a GI, right? So you have a GI. And then what are you ending with this GI? Okay, I probably should do it like this. It's going to be a little bit long. It's another for loop, because the GI in the original expression is ended with whatever is in the parentheses. So by itself, it is another loop. But this time I'm using j as my indexing variable. So j goes from I plus 1 as long as j is less than or equal to n plus j. And what do we do inside this particular loop? Oh, it's just the PIs, right? The PJs. So we have all the PJs here. Close this, close that, and then we have a regular OR here, and then there's a second component, which is K0, right? And then we have another for loop. So we have another for loop. I goes from 0 to n, like so, and these are all just the PIs, like that. In other words, you know, if I were to convert the closed form into a loop structure that you are familiar with, it'll be something like this. Okay. Now, obviously, you know, you cannot have a conjunction with the result of the for loop. I'm just using that as a notation. Okay. Okay. So, but going back to here, we can actually do a little bit better because we know n is 2. So we're going to substitute all of these things with 2. And we'll go ahead and expand it. Okay. So we know that there are 3 iterations, you know, with this loop here. There are 3 iterations. The first iteration is going to be G0. What else are ended with G0? When I is 0, J starts with 1, and it will end with 2, right? So, but those are all ended with PJs. So it will be P1 and P2. Okay, G0, P1, P2. That's the first iteration. Well, actually, that's the first iteration of the outer for loop. What about the second iteration of the outer for loop? I would have a value of 1. Okay, so we'll start with G1 here. And then when you look at the inner loop, I is 1 already. J starts with 2. So when J starts with 2, you only get a P2 because you won't get a P3. Because you have the exit loop when J is greater than 2, so that's why you don't get a P3. So that would be the end of the second iteration. What about the third iteration? In the third iteration, I has a value of 2. Okay, so we always have the GI, so we have G2 in this case. But when you look at the inner loop, we won't even go through a single iteration. Because when I equals to 2, 2 plus 1 is 3. So J starts with a value of 3 already. but the condition to stay in the loop is j has to be less than or equal to 2, which means we exit the inner loop right away. There won't be any p components in the third iteration. Is that okay? All right. So after this, okay, after this bunch here, we have a regular OR. Okay, so we write this OR here. Okay, I use all the wrong operators, but plus is OR, in my notation, so it's not bad. It's just not consistent. Okay, so now we have K0 and the result of this for loop. Okay, K0 is going to be a part of that equation, but when you look at this loop here, okay, so we have 3 iterations because I goes from 0 to 2. And for each iteration, we're just pulling one P component out of the whole thing. So we end up with P0, P1, P2. Is that okay? Does that match what we had? Let's double check. I haven't double checked yet. So let's see. Pull this one all the way to the top, and then we cross check G2, P2, G1, P2, P1, G0, and K0, P0, P1, P2. So the ordering is a little bit different because of the way I append the terms, but all the terms are here. Is that okay? Is that a proof that the closed form is correct, just because it works with K3? Nope, it's not a proof. Now it is a validation, okay, that at least it works in one case, but it's not a general proof that it does work in general. Now, for those of you who have taken 440, it doesn't have to be from me, okay, what kind of proof technique are you going to use if you are asked in cisp 440 to prove that if ki has this recurring relationship with the one before, how do you prove that this definition will lead to this closed form? What proof technique are you going to use? Wikipedia, by the way, is not one of the techniques. Neither is Quora
Is it
or
proof by
Reddit.
induction?
Huh?
Proof by induction?
Proof by induction, very good, because it is, it is proof by induction because the relationship between K and Ki plus 1 and Ki is recursive. Anything that is recursive lends itself to proof by induction. Good job, okay? Now, in this class, we are not concerned about the proof, okay? The inductive proof that this theorem is actually correct, we're not too concerned about it, okay? But I do want to relate things in this class to stuff that you might learn in your other classes. Why is that? Huh?
We might take those other classes.
Well, this is incentive for those of you who haven't taken to know that, oh, so that other class here will introduce these topics. What about those of you who have taken 440 already and is trying your best to forget everything you learned in 440?
You won't let us let it go.
I will not let you let it go, and why is that? By the time you get your associate degree over here, are you done?
No. Go out there, gotta use it again.
Yep, exactly. And the more you interrelate the concepts that you learn from your different classes, the more
Familiarize yourself.
exactly, the less likely you will forget about something, because now you're in your head, in your mind, you have multiple pathways to go from one concept to another concept. Okay, that's one thing. 2, what about the ability to apply the concepts? The more you interrelate the concepts, the different concepts that you learn in different classes, and see how they connect, the more you will be able to apply techniques from all the classes that you have taken to solve new problems. And why is that important? What do you envision that you'll be doing as a developer, or whatever job you want to take on in computer science or related industries? Are you first of all, are you going to be given a manual, an operation manual, and you just be following the manual to perform some mundane task? Is that going to be what you'll be doing?
If
You'll be dealing with problems that did not exist yesterday. And the due date is 2 weeks ago. That is going to be the nature of your jobs. Okay, the nature of jobs are changing very, very rapidly. 20 years ago, okay, I'm old. Okay, so when I graduated from university, most people are looking forward to a cushy job at HP, because back in those times, HP is still a very good organization, a good company, where jobs are fairly secure, it's cushy, it's not like really, really pushed. Okay. But when you guys go out, by the time you're done with your bachelor's degree, with a 4-year degree, what do you think is going to happen? Are you going to be hired by companies? Are you going to be employees? The chances are, it's less and less and less likely that you will become employees. You'll become contractors working for these bigger companies. You'll be a contractor working for Google. You'll be a contractor working for Intel. But you are not a Google employee. You're not an Intel employee, which means they will contract out a particular thing for you to do. But after that contract is done, there's no guarantee about the next project. Okay? So the nature of what you'll be doing will be changing. You're not going to work on the same thing over and over and over again. Okay? Every job will bring something that's new. Every job has a new challenge. You might need to learn a new language just for a particular job. That is going to be the nature of jobs in the computer science area in the next 10, 20 years. Okay? I don't see anyone being particularly excited. This is like, yo, yeah, yes, okay, this is the kind of job that I want. Well, just imagine all the things that you'll be learning, that you'll be exploring, and all the challenges too. So, if you're the kind who likes to experience new things and to solve new problems, the future is brighter than ever. Okay. Especially if you get into computer security or AI, the field of AI and the field of computer security, those will be changing faster than most people can keep up. There's no question about it. Okay, well, what is the most problematic thing that can come out of North Korea? It's not their ICBM, nor the nuclear warhead. It's their hacking, cybersecurity. Just think about it this way, okay? I'm not promoting you guys to be anxious and whatnot, but if you think about it this way, okay, this is something that I talked about with another person another day. Okay, you guys know how self-driving cars are becoming reality. It is reality now with some quirks, right? With some bugs to work out. And most people think about, when they think about autonomous vehicles, they think about Teslas, okay? Because that's kind of big on the news right now. And what is Tesla working on? In addition to sedans and SUVs and stuff like that. Trucks, okay? 18-wheeler sized trucks with a range of only about 200 to 300 miles. So they still have ways to go before it becomes actually commercially viable. What is Uber working on? Self-driving trucks, 18-wheelers, diesel-based, and those guys can go a long way, right? And they're self-driving. And do you think they maintain radio silence when they're self-driving? No, they keep chattering with the space stations all day long, and they might even park on the side, do a self-update, and then continue the journey and whatnot, right? So they're capable of being updated, anytime basically. Okay. What do you think 18-wheelers are capable of carrying or towing? Everything from chemicals to household items to UPS stuff, liquefied compressed petroleum gas, okay, gasoline, that sort of thing, right? What's going to happen if some hacker from a different country is able to remotely gain control of these quote-unquote autonomous vehicles? And we worry about people driving a truck into a crowd. Imagine what's going to happen when one of these things run into a shopping mall. So you're talking about AI, we're talking about computer security, we're talking about ways of using these things that many people have not thought about. But we need to think ahead of time, right? So that is what your jobs will be like, is to think ahead of time. Yep, go ahead.
Could be hijacking the trucks and getting access ports to the mainframe that drives them.
Exactly. And they can plant the back door way ahead of time before actually making use of the back door. That is the biggest problem. Is they can coordinate things. They can backhack everything and then set a time when they have a coordinated event that can hit multiple targets all at the same time. Okay? One of these things run into a shopping mall is definitely bad. But if it takes out the power grid, it's actually worse. Okay? So these are the things that you will have to deal with. Okay? I'm old, I don't have to deal with that anymore. Okay? But you guys have to deal with it. Okay? Because these are all new things that were not possible before. Okay? And AIs are they're thinking about solutions that we cannot even think about. Okay? A lot of times they have to unplug an AI because, okay, I think this has gone too far. Okay? Because the AIs can talk to each other in language. They can invent their own language to talk to each other. That's a little bit too much because we cannot leave the AIs to talk to each other and not know what they are talking about. Imagine the consequences of that. So I know this is not related to assembly language programming, but I do want to point out, your future has to do with being able to solve problems on the fly, and you have to deal with things that you have not been taught, that you don't even know existed the day before you got your assignment. It's like, okay, we need to do this. What is that? Okay, these are all new things. I haven't, learned all of these things from school. Yep.
Is the nature of having to pay attention so in controlling like AI so much, or trying to put it within parameters and regulations so high just because of the implication of how big of event and how big of an effect it can have on the rest of the world, just because of the nature of how much of an impact it can have.
So your focus is on regulation, or
yeah, like if like the example you said, shutting some AI down when it begins talking to other AI, making its own language,
right?
And we're trying to regulate it, and we're like, hey, stop it, so we turn it off. Is it because of how far and how much of like the impact that the AI could have on the rest of the world?
Yep.
If it was to get out?
Yeah, things that were not even possible, or people thought was not possible, is now happening. In the arena of AI, you guys know that Elon Musk's OpenAI played Dota 2 and beat a top-notch human player on the 1v1 game, and they're now working on StarCraft. Okay, they're progressing, closer and closer to actual combat warfare, kind of planning. So, when you think about the movie, what is the name of that movie?
Terminator?
No. That's. I'm not too concerned about that one. This one is.
War games?
No.
What's the movie?
Ender's Game.
Oh,
Okay, Ender's Game. Remember at the very end of Ender's Game, people go like, "Whoa, we didn't know that he was actually, commanding all these ships to almost commit, genocide on that other race, because to Ender, it's just a game. Okay, it's almost like just a regular game, but we can take it one step further. Okay, he may be playing against an AI, and the AI is learning his tactics. Once the AI learns his tactics, the AI can reapply that tactic to as many times as it wants. It would just be sharpening the AI's ability to apply all of those tactics without human intervention. That would be the last twist. Okay, if I were to add a twist to Ender's Game, is he's not playing, he's not actually commanding the ships. He's playing with an AI, and the AI is learning from him, about all those tactics. And it's already happening. Okay, so you guys really need to keep in touch with all of these latest and greatest development, because every single one of these things is a little dot connecting to the future that you'll be in. Okay, and the more you are in touch and the more dots that you're collecting, the better you can see the shape of how things will become in the near future. And I think that will help you prepare for that future. The more you know about the trajectory of the future. Okay, end of digression. Right, so getting back to the homework assignment. See, I'm switching back to something that's totally mundane and boring. So, general guideline of your homework assignment. So, first of all, I want you to use the carry look ahead method. And we're dealing with a 3-bit by 3-bit adder. So the first question is, do you have a need to apply the general closed form like this to figure out your case? Nope. Because I already spelled out what is K3, K2, and K1. And that's all you need for a 3-bit by 3-bit adder. Yay! That's good. You do have to implement the PI and the GIs. How difficult is it to compute the PIs and the GIs? One is an AND gate, the other one is an OR gate, right? Okay, cool. That's pretty easy. So this is where things goes a little bit strange, okay? Or you might need to explore this a little bit, because I want you to use or consider using multi-bit gates, okay? Which doesn't seem to make any sense, okay? Because a logic gate is a Boolean operation, which means it takes inputs, each one being a single bit, and it has an output which is also a single bit. Well, but in LogicSim you can actually have multi-bit gates, okay? So in today's lab, I will demonstrate what those things are, and you might want to think about how you can apply those things to help simplify your design, okay? Because if you use it correctly, you can use a multi-bit gate to greatly simplify your design in this homework assignment. It can save you a lot of time. Regardless of whether you use multi-bit gates or not, you will need to use splitters to split a single multi-bit wire or bundle into individual bits and merge multiple individual bit wires back into a bundle. So you will need to use splitters. I will show you guys how to use a splitter as well during the lab time. Okay? So next, you need to understand the general description of the equation of Ki, and we already have all the individual terms done, so you don't really have to expand it from the closed form. I do suggest the use of subcircuits to compute K1, K2, and K3, just so that your overall design doesn't get too busy. Okay, it's not needed. Okay, if you want to sprinkle your gates all around the whole design, it's up to you. Once you have computed all the carry bits, okay, the KIs, then the individual sum bit is just this. Okay, the sum bit I is the result of adding xi and yi, and you take this result and add it to Ki. Okay, this is something that we have seen already from last week. This means it's probably a good idea to implement the result function as a subcircuit so that you can instantiate multiple instances. And I'm going to add one more thing here. Okay, let me see if I can make changes. I guess I have to hit edit first. For this homework assignment, since we have talked about how to do this already, you are allowed to use exclusive OR gates. Okay, now this is a big deal. Okay, the fact that you are allowed to use exclusive OR gates, in addition to you can use multi-bit gates, can really save you a lot of design and stuff like that. Okay, so the trick is how do you combine the bits, how do you split the bits, and how do you best utilize multi-bit gates. Are we doing okay so far with this? Okay, I like that feedback. Well, trust me, it's better than what I did when I was in college. There was one time I fell asleep. I always sit in the front row, being short as I am, I always sit in the front row. And there was one time I fell asleep, just like usual. And then for whatever reason, I got startled. Okay, so I came to a startled, awakening. And I threw everything around me forward. But it was not a classroom like this, where only the person next to me would actually see, oh, okay, that did something. It was in the auditorium. So everybody go like, ooh, so there goes Tag. Yep. So I had my fair share of falling asleep in class. All right, so let's get back to the modules. Modules, where are the modules? Ah, right there. Still transitioning from Moodle. Okay, so once we're done with binary addition, now we want to move into binary subtraction. So the question is, how difficult is subtraction now that we understand what is addition? If you look at the length of the slide of subtraction, it's really short. Okay, by comparison, is really, really short. So as usual, I start with base 10 examples because those are the things that we know, right? We know these things left and right. So when you were a kid, how do you know that 9 minus 7 is 2? How did you learn that? Right, exactly. So you have a ruler of something, and you go 9 steps forward, and then go back 7 steps. You go like, oh, I'm only 2 steps away from where I started. Okay, that's how you learn 9 minus 7 is 2. What about 9 minus 5? You have to do the whole thing again, and then count, oh, I'm 4 steps away from where I started. So you learn about the subtraction table by doing things physically, okay? And then you start to get into things that are really hard to understand. What is 2 minus 7? Okay. Well, if you look at 2 minus 7 now, you can go like, oh, okay, that's negative 5. But we don't want to look at this as negative 5 because looking at 2 minus 7 as negative 5 doesn't give you the ability to do multi-digit subtraction. So what do we need to look at this as?
7 minus 2.
It's 5 with a borrow. We have a borrow. Instead of a carry in addition, now we have a borrow. You got $2 in your pocket, and then Tag comes by and go like, okay, I want you to give me $7. You look at your own $2 and go like, well, that's not enough. You want your grade or not? Then you look at the next guy and go like, okay, you got a 10? Yeah, I got a 10. So you borrow a 10 from the next guy, so now you have $12 total, so you can give me the $7. But once you give me the $7, the subtracting of the 7, then you have $5 left in your pocket. But you also have to remember that you owe the next guy one $10 bill. That is the whole concept of borrowing. Is that okay? But how do you remember all of these things? Okay, 3 minus 4 is 9 for the borrow, and so on. How many entries are there? Technically, we have 100 entries, right? Because you have 0 to 9, you have 0 to 9, and then each one is one particular single-digit subtraction. Some people get smart and go like, yeah, but we know that whatever minus 0 is that whatever. Fine. Take out one column. But you cannot use symmetry. You cannot use symmetry in this case because with addition, you can have the number of entries that you actually have to memorize because addition is commutative. Subtraction is not. So you can't just say, okay, I only have to remember half the entries. So you have 80-something, at least 80-something entries that you have to memorize when you're dealing with base 10. Can you imagine the enthusiasm? Yeah, go ahead.
I don't know how you got the 9.
What?
3 minus 4, 9.
3 minus 4, oh. Yeah,
Yeah, 13 minus 1. 13 minus 1.
Yeah.
Oh, okay. Okay, I see.
Yeah, just imagine you got $3 in your pocket. I asked for 4, but you can borrow a 10 from the guy next to you.
We're looking at both of them.
Okay. So this is a big table, huge table. And then you think about binary, okay, base 2. How big is that table? That's it. That's the whole table. 0, 1, 0, 1. And we can even spell this out entirely, right? 0 minus 0 is 0. And does it have a borrow? Okay, so we'll say borrow equals to 0. Is that okay? What about 0, 1 minus 0? This is 1 minus 0 as a result of 1. Does it have a borrow? No, so we'll call it a borrow of 0. We'll deal with this one first. 1 minus 1.
0.
As a result of 0. Does it have a borrow?
No.
Nope. So this is the only one that's kind of tricky, right? Because we have 0 minus 1. What do you think it's going to look like? Okay, 0 doesn't have a 1, right? So you have to borrow. But what are you borrowing? What quantity are you borrowing? You're borrowing 1 of what from the next digit?
1, 0.
You're borrowing 1 of 2 from the next digit. You take away the 1 that you really want to give away, you got 1 left. So the answer is 1 with a borrow of 1. Is that okay?
Can you say that again?
Okay. So you got no money in your pocket.
Okay.
And I say, you know, if you want to grade, give me $1. You go like, okay, I'm gonna borrow. But when you borrow from the next digit is representing each one of the next digit is twice the quantity of what you are dealing with.
Yeah.
So when you borrow, you're borrowing a 2. You give me 1, you have 1 left.
Yeah, okay.
And that's why there's this one. It is the same thing as in base 10. When you have 0 minus 1 in base 10, you have a 9 with a borrow. It's the same idea. Because when you have nothing and you have to give me $1, you have to borrow. But in base 10, when you borrow, you're borrowing 10 of what you are dealing with. So you're getting 10, you give me 1, so you have 9 left. Is that okay? But that's the entire table. Can you imagine that when I propose to change our numbering system from base 10 to base 2 to elementary schools, can you imagine how the kids will respond to this? They go like, yeah, we can master addition and subtraction in a week instead of months. And you cannot make mistakes that easily either because there are only 4 entries. Yeah. Okay. But we are more concerned about how to do all of this stuff using logic gates, okay? Because we want everything to be doable in a computer, right? So how do we do all this in the computer? So the next thing we want to do, I'm going to use a notepad here to do this. That's not my notepad. That's my notepad. Okay, so the next thing we want to do is to look at, okay, this is x, this is y, this is the borrow of x minus y, and this is going to be the result of x minus y. In other words, we are only putting all those entries on the whiteboard slightly in a slightly different way into here. 0 minus 0 has a borrow of 0, also has a result of 0. 0 minus 1 is the only tricky one, it has a borrow of 1, also has a result of 1. 1 minus 0 has no borrow, a borrow of 0, and it has a result of 1. And then we have 1 minus 1 having no borrow, and the result is also 0. Is that okay so far? It's just another way to look at this subtraction table. Is that okay so far? Yes? Okay. Well, you can kind of see that these are all, it seems like they can all be Boolean operations because they only involve zeros and ones. Okay? 0 is false, 1 is true. And then you look at the R column, you go like, yeah, we got this. Because it is identical to addition. So let's not worry about the result of a subtraction. The borrow is one thing that you go like, that's not the same thing as carry. We need to work on this one a little bit. Okay? So the question now is, how do we implement the borrow function so that it will give us 0, 1, 0, 0, given the values of x and y being like this?
Why if not x?
Yep, exactly. Not x, y. Okay? Or to be exact, using spelling out every single operation, it is not x and y. Because with not x and y, the only time not x and y is going to be 1 or true is when x is false and y is true, which matches what we want as a borrow function. But the important part is, it is doable using logic gates. Is that okay? Yeah, R has not changed. R is still the same. Okay. Cool. And we got about 7 minutes left. That's plenty of time to talk about borrow look ahead. In other words, how do we do a subtractor that uses the same kind of mechanism as a carry look ahead adder? Okay. So we fast forward like that, because we talked about all this stuff already. We fast forward to this. Ugly stuff. Looks ugly, but it's not. Okay. So we look at the borrow bit to column I plus 1. I use T just so that it's not B again. Okay, so T is kind of analogous to the K, and B is analogous to the C. Okay. So now we look at this and go like, okay, xi minus yi can contribute a borrow of 1. On the other hand, qi minus ti, which is the borrow from column I, can also generate a borrow of 1. Okay? Just like you have 2 sources of carry, you also have 2 sources of borrows. And they are related exactly the same way because each one can contribute to the borrow of column I plus 1. But you remember that borrow is defined differently. Okay, so this expands to this, and then this expands to this. Qi has not changed. If you look at Qi by itself, it is still the same as before, which is this part here. But now the way we treat this expression is well, I wouldn't say entirely, but it is quite different from how we did it with addition, because now you have a negation on the outside and a disjunction in the inside, which means to solve this you have to use De Morgan's law. De Morgan's law is kind of like distributing the negation. So this negation gets distributed into the individual terms, okay, being this one and this one. So you can see how these 2 terms are both negated. But then we have to change the disjunction into conjunction, which is implied here. And then you look at this and go like, well, I guess we have to apply De Morgan's law again. So this time we're distributing this not into xi as well as not yi. Not yi is just yi, not xi is here, but you have to change the conjunction into a disjunction. And then we do the same thing with this portion here, which becomes this. And then we use distribution. We multiply all the terms out, we end up with this. But when you end up with this, you notice certain things do not seem to make sense, or it is easy to resolve. Not xi and xi is guaranteed to be a false, because at least one of these 2 is always going to be a false. Okay, if xi is true, not xi is going to be false, and vice versa. So we can simplify that to a false. Same thing applies to yi, not yi. It is also guaranteed to be a false. We take those out, and then we are only left with this part here. Are we doing okay so far? Okay. So I used the same trick as last time. I introduced conjunction with 1 or conjunction with true. And this time I got a little bit smarter. I just say that true is the same thing as true or whatever, right? So I just decided to add 2 ti terms. Okay. And then I use distribution. So once I use distribution, this entire thing becomes this thing here. And then I reorder things a little bit. And once again, after reordering things, I end up with this, and then I notice that not xi is common, so I factor that out. And then I'm left with yi or not yi on this side, and then on this side we have not xi or xi. Both of those will fold into a true, and then it disappears. So the bottom line is we end up with something like this. Does that look familiar to you? It looks like something that we have seen before with a twist, right? Other than the negation, they're the same as before. So what we do is we redefine, okay, for subtraction, we have to redefine GI to be not XI, YI. We have to redefine PI to be not XI or YI. That's the only change, okay? We negate the X, but the rest stays the same. Okay, so you go like, okay, what is the big deal? Well, once we redefine GI and PI the way we do it here, we end up with something like this. I hope you recognize that. Because other than K used to be sitting where T is, it is the same. So you would imagine, T1 would look like K1, and then T2 would look like K2, T3 would look like K3, and so on. And you're right, okay? Because structurally, they are identical. So when it comes to K100 or T100, you can use exactly the same structure, okay? And there you have your borrow, look ahead subtractor. Can you guys see how subtraction is really just one negation away from addition? Now, a lot of details goes into this, okay? But in the end, it is just one negation away. Are we doing okay so far with this? Yes, go ahead.
For the P term in the addition, did it go to N or N minus 1?
I thought I updated this. This should go to N too.
Okay, so
Yeah.
it's supposed to go to N?
Yeah, I just haven't updated this one yet.
Okay.
Yep. But good thing to point out. I'm just gonna point out the whole class. This -1 is not supposed to be there. It should be just N. Okay. So we are done with addition and subtraction, but we are still missing one big piece, which is what we'll be talking about on Thursday. What about negative values? It's great that we can now deal with addition and subtraction. We can do carry and borrow and stuff like that. But what about negative numbers? Okay, when you only have zeros and ones, okay, how do you represent a negative value? Yes.
2's complement.
2's complement, exactly. So 2's complement is going to be the mechanism that we use in order to convert the minus something into the negation, into a way that we can represent. Okay, very good. So that's what we'll be talking about on Thursday. All right, so I'm going to give you guys a break of about 10 minutes, and then I'll start the lab section to talk about the multi-bit stuff and the splitters and the mergers.